Yeah, hello and welcome everybody to the second session on hierarchical task network planning in this conference. So my name is Daniel Höller. I'm from Saarland University and I'm the session chair for this session. First talk will be by Mohammad Yousefi, Mario Schmautz, Patrik, Haslum, and Pascal Bercher, and it will be on the incompleteness of a star search in totally ordered HTN planning. So do you want to come forward?
Thanks, Daniel, for the introduction. Hi, everyone. My name is Mohammad, as Daniel mentioned, and I'm representing on behalf of our team. In this paper, we've studied the theoretical properties of A star, namely its incompleteness for HTN planning. And unfortunately, the result holds under very severe restrictions, as we'll see. I assume that you're all familiar with classical planning. Basically, you have a formalism, you have a goal, and the goal is to find a sequence of action that achieves that goal. HTN planning basically extends this goal-seeking behavior with some grammatical constraint and solution string in a way that you can also express behaviors on how to achieve the goal, not just the goal itself. So it's more procedural in a sense. And as I mentioned, this is done via formal grammar. An example of this would be this simple routing problem that we have. Suppose we have a truck at L2 and we wish to drive to L4, which in classical planning is just one single step action to drive from L2 to L4. But in HTN, as I said, every solution must come from a grammar. And in our studied case, this is a context-free grammar because we restricted ourselves to the totally ordered problems, which is decidable. So this result is more bizarre because the problem has a solution and it is decidable and should be technically possible to find it. So the structure of the grammar is that we have basically 3 decomposition rules, which we call methods in HTN planning. If you're in an adjacent cell, like the case is in the problem depicted here, then you just execute a primitive action. But if it's a long horizon task, for example, from L1 to L4, then you can convert one compound task of one compound instance of drive to 2, so that you can basically duplicate the driving task. And if you're already there, for example, if the truck is already at L4, then you can just remove that task and consider it a go. The problem is the intersection of this duplication and these empty methods really creates some interesting scenarios in A star, as we'll see. And the simple solution that just do one single action to reach the goal is not, A star may not find it, even if it has the perfect heuristic. So just a quick recall of what A star is. It's basically a loop of node selection and expansion based on some f value. The node selection is just pick a node which has the minimal f value, which is the combination of the cost incurred so far and an estimate of how far you still need to go. An important distinction that I must mention is that the search nodes now have, in HTN planning, are not just estates. They are a combination of task networks and estates. And as you'll see, this is a very crucial difference. And we don't really need the estates to achieve this incompleteness result. It comes purely from the grammar. And the node expansion function that we've studied is basically progression, but this also works for decomposition if you're familiar with that terminology as well. The idea is that we pick a node. If it's a goal node, then we call it a solution. Otherwise, we analyze the first task of the task network. If it is a primitive task, we execute it if it's executable. Otherwise, if it's a compound, we progress by basically considering every possible method and decomposition that are available for that single task. And once A star terminates, it returns the optimal solution. All right, so going back to the example that I have about driving, so we have simplified the names a little bit. T is basically the compound drive task, and X is just the primitive drive task that we have. And the three decomposition methods that were introduced for short-range driving, long-range driving, and if you're already in the goal. So let's see how it actually behaves. We have this initial node. It consists only of one compound task, which is the drive task. The perfect heuristic correctly estimates that you need exactly one single unit cost action to reach the goal. So since this is the only task, we pick it from the frontier and expand it into all three decomposition methods that are present. And so the node with basically no tasks in it is already pruned by the perfect heuristic because it cannot achieve the goal. We need one drive action. But we have two possibilities here. One is the primitive drive action. The other one is a duplicate of the compound task. And interestingly, they both have the same exact F value. And in order to see that, let's just progress the search and see why that's the case. So if we expand the node with the X action, we expand the goal, and then things might work based on the tie-breaking strategy that we're utilizing. Otherwise, let's see why this one has still an H star value of 1, because we have already duplicated this. Let's see how it behaves. Once we expand this, there are, again, three possibilities. One is to, then the most important one is the last one. We can basically remove the compound task using the empty method. So we go back exactly to the initial node with 0 cost. We have created a duplicate node, a duplicate task, and we can just also freely remove it. So the H value is still 1. But on the other hand, we can convert one of the first task to a primitive drive action. The H value does not change because we can still remove the last task. And otherwise, we can also create another duplicate and have 3 compound tasks, and all of them can be removed, basically. This structure keeps repeating, as you can see. And an interesting property is that the closed list can actually detect that, for example, from this scenario, once we remove the T, we're again back to the original place that we were in. So a counterintuitive implications of the theorems that we have proved is that having a closed list and doing graph search is actually much more powerful than having the perfect heuristic in HTN planning. Determination guarantees are much tighter. And that's basically how it continues. And the problem is that once we can also grow this. So the closed list cannot really rule out every possible scenario. So it can grow indefinitely, as you can see. And we have this 0 cost return to the initial node whenever we want. This means the H star heuristic is actually blind on this path, and this is an infinite 0 cost path, which is a sufficient condition for the incompleteness of A star. That's the teaser. We have classified and identified a few different type of cycles in this grammar that can happen, and the amount of trouble that they can cause. The unrestricted cycles are basically any compound task that is recursive, namely that it can reach itself through decomposition. A perfect heuristic with a 3 search A star is incomplete with this unrestricted cycle. But the more interesting problems, a lot of these things can be avoided with actually graph search. The epsilon prefix cycle is when a compound task can recurse without introducing any new primitive action before it as a prefix. This is very much left recursion in formal grammars, if you're familiar with that. And it is very problematic. And over epsilon prefix cycles, we can introduce more restrictions. For example, the empty cycle is when you have this left recursion, but in order to recurse, you do not need to introduce any suffix either. So you basically keep repeating the same task without actually doing anything, neither growing nor shrinking the task network. The problems start when you can grow the things, because then your closed list cannot determine the duplicate task networks. A growing epsilon prefix cycle is actually left recursive with the addition that whenever you recurse, you introduce some suffix of tasks, and the mildly informed heuristic can detect that this task network is growing. So that actually can be ruled out. But the most problematic one is the grow and shrink cycle. This is basically the thing that I've shown in the previous slides. You can grow the task network, but at zero cost, you can also remove this newly introduced suffix. So that is the thing, that the grow and shrink cycle is actually a major problem. And we have also analyzed the IPC domain, which I'll get to in a moment. But the summary is that A star is incomplete for HTN planning. And as we have shown, this holds even for one single action and one single compound task. So this is not merely a theoretical construct that will never have it happen in practice. And the behavior of this drive mechanism, for example, is a very practical thing that actually is of practical use case. So in total, A star is incomplete, even if you have the perfect heuristic, even if the problem is undecidable, and even if you have one single unit cost action. So these problems need to be considered before deploying this algorithm for HTN planning. We have also shown that detecting whether this can actually happen in a problem, these cycles can be initiated in the search, is as hard as planning itself. So that's another issue. But we have introduced some approximations on whether these cycles are present or not. One can always restrict to recursion-free grammars, which would solve the problem, but this also very much limits the expressivity and the kind of problems that you can model with HTN planning. I have something that is a little bit more optimistic is that we have found that the Greybach normal form can actually resolve this problem if we manage to achieve that, but it is exponential in size, or in the naive case, it's at least can be exponential in size, but at least finite is better than incomplete. And the next thing is that the conditions for incompleteness actually holds in a lot of IPC benchmark domains of the HTN planning track. So there are only 2 domains that do not have any form of recursion out of 23, I guess, domains that were present in the IPC domain. And 12 of these 23 domains have zero cost recursion, meaning that they do not introduce any primitive task to do recursion. But again, they differ based on whether it's an empty cycle, which does not introduce any suffix, or whether the task network actually grows. And the grow and shrink cycle, the most problematic one, is actually present in 2 domains meaning that even if you have A star with the perfect heuristic, it cannot solve every IPC problem that is out there, which is a major issue. But as I said, some of the grammar transformation techniques can resolve this problem. And that's it. Thank you very much for listening.
Thank you very much for this interesting talk. So are there questions?
I guess my question is, could you not fix this problem by simply breaking heuristic ties with the smallest resultant network?
That's a good thing, a very good question. We've actually studied that, and the answer is that only works if you have the perfect heuristic. Let me bring back this thing. If your heuristic is slightly off, meaning by an epsilon off on any of these nodes on the main path that we have, then your f value is actually less than the optimal cost. So the A star will keep working on that node until it resolves it, which it never can. So that tie-breaking strategy only works if you have the perfect heuristic. Any amount of like an epsilon away from that does not work.
Thank you.
A directly related question. So I was wondering, so you are doing A-star search, so I'm assuming you are targeting like optimal search or something, and what you estimate with your perfect heuristic is not goal distance, but it's action cost, right? As you would do in such a setting.
Yeah.
Could you tie break by the path cost as heuristic?
Again, the tie breaking has very limited, I would say, implications in here, because the f values will remain less. Again, if you're doing suboptimal search, then maybe you can do that, and you can do a lot of other things. But for optimal search, tie breaking won't help. But for suboptimal search, I don't have an answer that I'm certain of. It might or might not help. We haven't studied that.
So at this point, I think I'm echoing some of the things that I said before, but there are other, I mean, A-star has been known with inconsistent heuristics, it's far from optimal. And so there's other algorithms like breadth first heuristic search that would actually do a breadth first search. In the case of the perfect heuristic, it would do the breadth first search instead. And there's other algorithms like budgeted graph search that solve the worst case. So I'm just wondering if you thought about any of those algorithms. Obviously, if you have an infinite number of nodes below the optimal solution cost, you're never going to find it. But I just wonder if you thought about those other algorithms.
We have studied BFS to some extent, and I think we haven't in this paper, but I think it's to some extent well known in the literature that it is not optimal, because that would optimize the depths of the solution. No, we haven't then. Yeah, and that's the case for us, I guess. There are infinite, but it's a pass, so yeah.
So one other quick question. So I was a bit surprised by your empirical results. So I know that a lot of the benchmarks from the IPC, if you look at the decomposition as a grammar, they are not self-embedding. So they are describing a regular language, and you can prove that. I'm not aware about the distribution over the domains, but like 2/3 of all problems in the IPC are actually classical planning problems. And so I was wondering whether your criterion overlaps with this self-embedding. Do you know?
I'm not familiar with the term self-embedding.
So if you look at a strongly connected component, the question is whether while looping that, you can only generate symbols on the right or on the left. And if you generate symbols on both sides, you are self-embedding, and then you have no other. So if it only goes to one direction, you have proved that's a regular language, essentially.
Mm-hmm. So the way that we have done our study is a little bit different. We've created the TDG over the domain. And we have checked for cycles, whether there is any cycle and which compound task can initiate a cycle and terminate a cycle. So that's how we came up with this, but your metric is a little bit different. But so this part is, I think we needed to kind of consider the prefix and the suffix, because we wanted to classify based on whether you can do recursion without introducing a symbol or with introducing a symbol, because that also makes a lot of difference in here. And yeah, I think only 2 of them, and we actually 2 people independently verified that. So I guess
Yeah, maybe you can have a look into this.
Yeah.
So
Okay.
let's thank the speaker again.
Thank you.